All right, so now we're talking about the solutions to the Dirac equation. Also, there's a new plant back here. If you like plants, hit subscribe. Anyways, so we're going to talk about the. So let's recap what the Dirac Lagrangian looks like. The Dirac Lagrangian looks a little something like this. So we have L Dirac. Keep in mind that this is a free, we're talking about free fields right now. And free fields means we don't have any added potential terms onto these fields. There's no interactions, right? There's no interactions going on with these Lagrangians. Interactions are going to come in chapter 6 when we're going to talk about interactions, and those are going to give a lot of richness to quantum field theory. We're not there yet, though. We want to really establish. We really want to understand the Dirac Lagrangian. We really actually want to understand these Lagrangians in their free form without interactions before we consider the interactions. Because considering the interactions again is sort of like a prereq before we get into interactions. Anyways, so our Dirac, we're recapping our Dirac Lagrangian looks a little something like this. And that gave rise to our Dirac equation, which was, that's our Dirac equation. So now we ask the question, what are the solutions to this Dirac equation? All right, so we go from Lagrangian to equation of motion. To get to this point, if you recall, we used the Euler-Lagrange equations. And then we propose some solutions here. So what I like this diagram I've sort of made. Where we're going to have spin-up solutions. We're going to have spin-down solutions. Okay, and out of the spin-up solutions and spin-down solutions, we're going to have real solutions and complex solutions. Okay, so what do these look like? So our fields, we're going to give them this symbol again that we've been doing. Make that a little bit better. So for our spin-up solutions, we're going to have a complex solution and a real solution. And there's going to be components on these things. And the components we're just going to call U1 for right now, and V1. Okay, so we don't know what these are yet, but the idea here is that we want linearly independent solutions. And again, we're really just proposing something, right? We're proposing something and we're going to see if it works. And for our spin down solutions, these are going to have a 2 subscript on the bottom. Again, this is all out of the book. The book doesn't give this table. right? I sort of made this table myself, but this is a good way of organizing your thoughts or organizing the material. So the 2 denotes spin down solutions. Okay, and then we're going to say e to the minus I mt and e to the minus I mt, and then e to the I mt and e to the I mt. So this is what we're proposing our solutions to look like. Let's see what these solutions do, right? So if we can, well, before I do that, U1, we're gonna say, U1 is, we're gonna say is equal to this right here, and U2 is going to be this. V1, again, V1 is going to be 1, 0, and V2 is going to be 0, 1. So all of these here are actually 1 by 4. These are four vectors, but they're not. What they're not, though, is 4 vectors of time, space, and time. Their components are not x, y, z, and t, and that's going to be important to know or to note, because when we consider space and time, we are fundamentally looking at these objects that depend on space and time, right? So when a point here and a point here, if you had a scalar field, for example, the scalar field might differ from here to here because of the change in space and the change in space between the two. Whereas these spinor objects, these things don't depend on space and time. What does the space and time part are these exponentials, right? And so we could see explicitly that we have this, we have the time, we have the time component here for all of them. Okay, again, we're just proposing this, and what I think I might do is I'm gonna go ahead and say that these work, okay? And again, you can go on to my Patreon page to check that these work, right? Because what you're going to want to do is you're going to want to put these solutions, say you want to put this solution in for here and see if it works. And because these are matrices, here's the point, not matrices, because these are vectors of some sort, they have components to them, we're going to see that this matrix, these gamma matrices, are going to concatenate those to a number, right? Because we have, again, these are 4 by 4, this is 4 by 1, right? So, well, not to a number, but you can see how it's going to work out, right? You could see how these are going to work out. Checking that explicitly is going to probably take another video. If you want me to do that, then go onto my Patreon page. Because that will take that'll take a whole video in and of itself. So we're going to say, so we propose these solutions, and we're saying that these solutions work, right? Which is kind of weird, right? Because I'm just telling you these work. But again, I'm giving you the point. I'm giving you the gist. I'm giving you the punchline. If you want more than just a punchline, then you can go to my Patreon page. if you really, really want to understand how this works. All right, so both these guys here, if you recall, those look like chi. These are the left chiral spinors, and these are the right chiral spinors. So what we can do, suppose now we had a solution that looked like this, and we're starting at time equals 0, right? So I'm gonna say I want to look at this guy right here, this right here, and I'm gonna put it at time 0. So what's that? That's u1 e to the 0. If I did the same thing for my adjoint at time equals 0, again, that's just going to be v1 at time 0. And so, putting these together, we're going to get that phi 1 at time equals 0 minus phi 1 at time equals 0. Let's see this is. You might think this is random, but let's take a look at what this ends up being, right? We're going to get 1, 0, 1, 0, right? Because e to the 0 is just 1, minus 1, 0, 1, 0. Well, what does that give us? That gives us 2, 0, 0, 0. This is very interesting because what we're able to do is we're able to, if we find the difference between the real solution and the complex solution to our Dirac equation, we find the difference between the two, we get this, we've essentially isolated out this unit vector. We get a unit vector as the difference between the real and the complex solution. This is something that the book goes through, and so the mere fact that we got 2 seems to suggest, well, if we did this, well, that's just going to be 1, 0, 0. Okay. Similarly, you can do the exact same thing with well, not with 0, not with 0. You can do this with pi over 2m, for example, minus t equals pi over 2m, like this. You can do that, and what you'll get is I times 0, 0, 1, 0. So what we're doing, well, this is actually pretty interesting. What we're doing is we're saying we have found that the difference between the spinor field, the real spinor field, say this is our real spinor field, at time equals 0, or at time equals whatever. So say this is at t equals 0, and then we also want to do it t equals 0 for these are our two solutions. We have two fields basically for these solutions. And when we take their difference, again, when we take the difference between these two fields, what we get is a unit vector, right? This is very interesting because what this tells us is that from time zero, suppose now we said that this was equal, this is the difference between our two fields at time equals 0. This here was the difference of our two fields when at time equals pi over 2m. What does this tell us? This tells us that at time 0, and we evolve in time, when we evolve in time to pi over 2m, we see that we went from 1, 0, 0, 0 to 0, 0, 1, 0. We did this evolution. We're evolving between basis vectors of the Dirac spinor. All right, so the Dirac spinor, again, is a combination of is a combination of our left and right chiral spinors. It's a 4-dimensional object, or has 4 components to it, and we can isolate. We can create independent basis vectors. Independent basis vectors within this 4-dimensional space by merely taking the difference between our spinors, between our real and complex spinors. This is something very interesting that the book goes into. Again, this book, No Nonsense Quantum Field Theory. This is something very interesting. And what we'll find later also is that the parameter m, this will determine the rate at which this oscillation occurs, because again, m occurs right here. So depending on what m is will depend on the rate of this oscillation. We're oscillating between basis vectors. And these basis vectors, it can be thought of as you have your spinor, right? You have your spinor, and as time evolves, the spinor oscillates between up and down states, right? This is very, very interesting, and you can do this you can iterate this also. Maybe I can do that in another Patreon video. You can iterate this process. You could start from 0 and then say go to pi, and then, or say go to like pi over 2 and then pi over 2m, and do the define steps between 0 and pi over 2m, and see how this thing evolves, right? That again, this is a free field, but these are solutions to the free field. This is what happens. Again, assuming we have a free field, this is what happens to spinors in this case. This is very interesting. And I'm pushing on 20 minutes here. I think that's good enough if these videos are a little short, but again, if this is the kind of stuff you're interested in, hit that subscribe button, and head on to my Patreon page if you're interested in looking at more details of this book. And I will see you guys in the next one.